I'm just going to try to keep that off into the corner where I can see what's going on. All right. So we have a system, right? And we're going to start off modeling it in the time domain, all right? And, oh yeah, that's great. You know, if you give me that, if you email me the Discord link, I'll put it in the notes. So we have a system, right? And we're going to start modeling it in time, right? And we have our inputs. And our outputs. Now there are some things that we'd like to mention, and all of the systems that we'll really be using in class are going to be linear time invariant, because ultimately we're going to want to use the Fourier expansions transform and the Laplace transform, and those don't work unless everything is linear and time invariant. All right. So what are the qualities of a linear system? And that's essentially if, you know, I have an input, right, and it goes from, let's say, 0 to 1. It goes into our system, and let's say now it goes from 0 to 0.5, right? If we scale that by a factor of 2, right, we put it through the system, then the output is scaled by a factor of 2. So the peak was 1 in this case, and now the peak is 0.5, right? Peak is 2, and now it goes to 1. And really, HT equals, in this case, Vn, or divided by 2. All right. So that's the scale property. Now, the next one is delay. So if we delay our input, right, so this was T1, right? Now we're going from 0 to 1 at T2, right? You can see that it's delayed, right? And that maybe my picture doesn't show, but it's whatever the system is, it's just delayed by that amount, all right? So the other one that we're going to talk about is that we can break up a linear sum. All right, so if I sum these inputs and then put it into the transfer function, right, that would be the same thing. That would be the same thing as summing it after the fact. And you're familiar with that from your circuits class. Superposition. All right. Now, so all right, so actually, if you guys could save the chat that goes directly to me for only questions about what we're doing right now, that'd be great. Because if the chat box, or actually, I might be able to put the chat box somewhere else and then it. Ah, okay. All right, I was able to put the chat box onto another screen. So we have a system here, right? And I want to actually solve this not with differential equations, right, but with phasors, which really means impedance. And so the impedance of a capacitor is 1 over SC, which if we only take the imaginary part, we will have 1 over J omega C. Omega is the frequency. J is an imaginary number, right? So the impedance of the resistor is the resistor. And I'm just going to call this Vn. Now, what you might not realize is that we've taken the Laplace transform of the time domain representations here, right? And now this is actually a Laplace transform, or you can go through the phasors, right? But rather than setting the frequency to some known value and getting, you know, minus a, minus A times J ohms, we're just keeping that frequency a variable. All right. And if this is node 1 and that's node 2, all I have to do is take the voltage division of that right, which ultimately gives me this. Okay. Right now, this is just a little bit of review. All right, but the chapters and the modules are all right there for you to find. All right. So now we have a system, right, which all right. Which gives me this. Now, I'm going to do this in more detail later, but this is just so we have a system, and I need to talk about static versus linear, or dynamic, yeah, static versus dynamic. All right. But this HT, right, right, that is the system. Okay. So if I put in a delta function or a step function or a ramp function, right, I'm going to get the impulse response, step response, and the ramp response of that system. So this is a, a system, right? I'm just going to describe it. HT, and it's actually that of a low pass. All right, but let's just do another system. All right. So now we have two systems to talk about, and this system is dynamic. All right. Oh. Sorry. Because it has an element or okay. The current voltage relationship in the time domain has a derivative. And so that means it has a memory, right? The way to remember that is even if I just have time and I have a point here and a point here, and I want to know the slope, right, which is the derivative, right? M would equal y2 minus y1 right? And then T2 minus T1. And so you need to know two values in time to calculate a slope, right? And so capacitors have this relationship, and it can be used to store energy or to be used as a memory, all right? But the thing is this system, right, we didn't really talk about delay, but you can have a system that's linear time invariant, but doesn't react instantaneously to the inputs. So this one has a delay, and it comes about because of that capacitor. And the capacitor, it's not just the fact that it's a C, it's just that the current voltage relationship has a derivative in it. All right. In this case, there's no memory storage element. There's no energy storage element, right? There's no S parameter or anything. And so whenever V in changes, V out will change instantaneously. And so that would be the definition of static. All right. And the op amps right? That you've studied in your prior classes have all been static, right? You probably have this memorized, right? But V out over V in for an ideal op amp, right? That's the whole point. Is given by this relationship, all right? And so an ideal op amp, right, will have no time delay, right? And this particular circuit, right, if the gain of the circuit is 2 and I put in 1 volt, I'm going to get 2 volts out, right? If I put in 2 volts and the gain is still 2, I'm going to get 4 volts. So it's linear, right? But that's an ideal op amp, right? But if I add these power supplies, right, well, that means this op amp cannot increase above or below those power supplies. So if R1 equaled R2, the gain will equal 2. All right. So let's just make a table. N 1, 2, 3, 4, 5. So one comes in, 2 goes out. 2 comes in, 4 goes out. 3 comes in, 5, 5, and 5. Right. Ideally, it would be 2, 4, 6, 8, 10. But the limits of the power supply, right? If the signal can't go over your power supply, then it'll be linear as long as the absolute value of V in Okay. So this brings out an interesting thing, is that most systems that we call linear have their regions where there won't be linear. Also, we talked about time invariance, right? If I put in a signal today or tomorrow, if I put in 1 volt, I should get out 2 volts, right? However, that's assuming that these resistors haven't aged and thus changed. And sometimes when you're flowing a lot of current through a resistor, its resistance can change as well, all right? So that means if I put in 1 volt today and 1 volt 10 years from now, I might not get the same exact voltage out. What tends to happen is, as long as you're within some specification, then that's okay, all right? But you can take almost any system that isn't a purely mathematical thing and find out some region where it's not linear. All right. Now, later on, okay. VDD is the power supply, all right? The positive power supply, right? All right. Minus VD is the negative. All right. So the op amps aren't like resistors, capacitors, and inductors. They need a power supply to work. All right. Although, yeah, many times in the circuits class, we don't mention it, but in lab, we do, although many people write their lab manuals so that you would never attempt to go over your power supply limits. And so it might never come up, all right? As we progress through the major, no, you're gonna run into situations where that's not gonna happen. I mean, not everything has been worked out for you. If we say design a circuit to do this, you've got to work out the power supply, the resistors, everything, all right? Now, we talk about an ideal op amp as having AV equals something like, equals infinity, Rn equals infinity. And yeah, but other things are the power supplies are plus or minus infinity as well, right? And so we just found out, well, no, that's not always the case. Now, Rn tends to be infinity if the other resistors are 100 times less than whatever Rn happens to be. And we are going to get into open loop gain not only not being infinity, but changing with frequency. And where this comes from is that op amps are made out of transistors, okay? Transistors are made out of diodes. Diodes have regions of holes and regions of electrons that are separated by a depletion region. And so if you have 2 kinds of charge separated by a dielectric, you have a capacitor. So every diode has some capacitance. So therefore every transistor has capacitance. And there's ones that I haven't mentioned. That means if an op amp is made out of at a minimum of 6 transistors, there's existing capacitors that exist. And these capacitors will make your op amp not work. The solution is a big capacitor. inside. All right. And in the homework questions, I will just say, is there a capacitor? There's a capacitor inside, or there's no capacitor inside. But if there is a capacitor inside, then it will have memory, right? It can still be linear. It just means there's a delay, but it does put a limitation on where the circuit will work, all right? But anything with a capacitor or an inductor has to be a dynamic system, because inductors store energy and so do capacitors. And so inductors have an integrative relationship, capacitors have a derivative relationship. And so integrating, you're having to integrate over time. So obviously there's a memory there. And taking a derivative, we already explained. Okay. So that was one particular system, right? That just for looking at it, you can't tell whether there's a capacitor inside or not unless I tell you. Now, of course, if it's a real op-amp, yes, there's capacitors inside it, right? That's not gonna change, all right? But just to reiterate, right? Current through a capacitor, voltage across an inductor, so I'm seeing derivatives. Those are memory storage elements. And so anything with one of those elements will be dynamic. All right. So any questions so far? And now again, I figured out how to put the chat bar to the side so I can see them as they come, and it doesn't throw me off. Or you could speak. Okay. So I did run out of time with discrete and continuous last time, so I just want to bring you up to speed on this. Now, whenever you see the word continuous, you should really also know that many people will call that analog. And many times they won't use the word continuous, they'll say it's an analog signal. And then the same thing with discrete, right? Continuous and discrete would be more the mathematical terms. Analog and digital would be more engineering terms. All right. Now, continuous values, that means the value can take on any number, you know, any precision, right? Any value, right? There's no jumping, there's no illegal values. So that's continuous. Discrete values are things that there's a jump between values that you can't You can't split the difference. Things like your electron energy levels, right? Those are discrete values, right? Now, of course, if you get enough electrons together, those values merge, but that's, I'll say that for MAD E153 and EE128. Now, a lot of times, most people only think of the values, either discrete or continuous or analog or digital, and that's the actual value itself, right? But then there's something else that we consider, and it's called continuous time or discrete time, right? And continuous time is that value can change at any time, right? Where discrete time, there's kind of like some event or clock that captures a value, and then it, and so it can only change at certain times, right? And like I said, these are the continuous and analog, the discrete and the digital. They are used like interchangeably. All right. I just said that. Ah, okay. Well, that's about what I'm about to do, Vicente. Okay. All right. So continuous time, meaning it can change at any time, and continuous valued. So that would be analog time, analog valued, right? The energy output from the sun, right? Now, sure, it might be within a certain range, but the intensity or the energy coming from the sun at any time is it's varying at whatever value it is, and it's changing all the time, right? Now, another thing about another continuous signal is if you're into vinyl records, right? When I put the stylus on that record, the bumps in the record move the the needle up and down, and that's spinning, and there's no mechanism that's letting the music out at any at certain intervals, and it's those bumps on the record are changing in a continuous format, right? If you're talking to your friends, well, I have to change it from IEEE room 376 to, oh, that's interesting, right? If you're physically in IEEE, you're continuous time and continuous valued. But if you're on the Discord server, well, everything's been digitized. It might seem like it's continuous, right? But in fact, it's discrete time and discrete value, right? And then live music, right? Now, what about physical measurements? Let's say we're measuring the output of the sun and we have some analog meter, right? Well, and let's think of it as a needle bouncing back and forth, right? So so now we're measuring it, right? And that analog needle is moving back and forth. And so it's still continuous time and continuous valuable, right? But if soon as I write down the value that I'm estimating wherever the needle is at, as soon as I capture that and say that happened, well, now that value has become discrete time and discrete valued. Because if I write down an intensity of 1.01, right, in order to be continuous, I'd have to have an infinite number of zeros behind that, right? And then I measured it at a particular time, and so it would be discrete in time, right? in this case, we have discrete time and continuous valued, right? And there's these circuits called switch capacitors. I think it's probably a bit much to talk about that today. But so I'm actually just going to let that part go, all right? But discrete time and discrete value, yeah, any signal in a microcontroller or PC, if the clock controls when values can change, right? If I have some average daily value, right, and I can't write down an infinite set of numbers beyond it, right, discrete time, discrete value, right? And you can see how this would look in time, like you have, 0, 1, 2, 3. They're not changing, right? That value, like it could be, the original signal might be changing, but once it's captured, right? If on day 1 I measure this and write it down, on day 2 I measure this and write it down, that is the value for the whole day, all right? So any questions on that? Okay. Now, I think a lot of times these questions, discrete time or discrete valued, they can almost get philosophical, right? The homework questions are, or at least they're straightforward now. There were some coding mistakes, which I truly apologize for. I'm not quite sure what happened, but it should be a lot more straightforward now, okay? I'm not quite sure what's going on today. I'm having a little bit of difficulty drawing. All right, now let's talk about integration of delta functions. And we're going to go, between our limits, right? So if I have time, right, and I have some limit A, right, and some limit B, then let's just give them values, +1, +5, and we'll draw our delta function and it's going to infinity at 3. Right? The way we describe that is delta t minus 3, because we delayed it from 0 by 3 units. All right. So now we want to integrate that from A to B and really one of these things that you just would remember is that from minus infinity to plus infinity, if we integrate a delta function, the area is 1. And again, what that allows us to do is I can have this as a delta function. I can have, that's ugly. I can have that feature as a delta function. I can have a Gaussian distribution as a delta function. Really, the area just has to equal to 1, and it has, the time of it has to be a lot less than the time of any system that you're working with. So really, we can just do this by inspection, because an ideal delta function, it's infinite in height, but it's also infinitely small in width. So this delta function is well within the limits, right? And so it's, in this case, it's going to equal 1. All right, let's do another example. Let's call this the delta function. That's 1. We'll call that 2. Right? So now we're going to keep the limits between 1 and 5. Right? And that delta function goes to infinity outside of the limits, and so it's 0. All right? And sometimes this happens in certain CAD software or certain Mathematica software where you you have a delta function here, and you integrate from 0 to something, and some packages will evaluate that to 1, some will evaluate it to 1/2, and some will evaluate it to 0, right? Because in fact, it wouldn't really be 0, it would be something called 0 minus, meaning just enough to the side to actually capture it, which isn't, which is not a mathematical way to speak. Okay, so yeah, Brandon, it's 0 because it's not within that 1 to 5 range, right? And let's see if I still have it up.
I have a question.
Yes.
What's the well, I mean, how did you get the 1 to 5 range?
I made it up.
You made it up? Okay. It's not something that you just find out?
um, right. I'm just trying to show you how to go about it, right? And so I'm just making up values where you can see what happens inside and what happens outside. But it's not like um, it's not a number like pi or it's not some special. Those aren't any kind of special numbers, right?
Okay.
Um, what I would say is that in a computer that's sampling something, right, there's a window in which it can capture the value and a window in which it can't, right?
That makes sense.
But I mean, I try to keep things as practical as I can, but then sometimes I'm just making up an example, right? And so if you look at the homework, right, here's a delta function, the limits are plus or minus infinity, right? So it's going to capture everything. Right? But now I've actually got limits. Right? I have a red and a yellow, and you can see, is it in or is it out? Now notice, right, this delta function is not really minus 10 units, it's infinity, right? You have to go from the scale factor there, right? Ooh, what's that? Looks like it's not inside. By the way, these homework, these all are randomly generated, just so you know, all right? But now here,
So
oh, excuse me.
so the bounds are just made up by the question.
Yes. I mean,
Okay.
actually, I don't, well, I'll get distracted, but yeah, you can
I get
see
it.
the code. Well, actually, you can't see it, but yeah, it's random number. It's random numbers that are generated so that the plots work out, right? But now in this question, we're actually multiplying these two things together, right? And so when a delta function is on its own, the area always evaluates to 1. And since the limits are infinity, no matter what this is delayed by or advanced by, it's still going to be 1. But then it gets scaled by whatever sign t is at. And you should be able to read that off. And it like there's like a 10% variance that you can have in your answer and it'll still be marked correctly, right? Then we have, same kind of question, but with limits. These ones, a little trickier, right? You have to really keep track. You have limits, but then we also have ramp functions and steps. And this one has ramps, all right? I think you would have seen these. Yeah, this continuous or discrete, I did a lot of editing of that. But here you have an ideal op-amp. So I'm saying it's ideal, except I'm giving you some things as the system dynamic, static, linear, not linear, and then the limitations are, right? And that, let's just say, yeah, there was some issues there. All right. But pretty much the giveaway is there a capacitor or not, right? That'll tell you whether it's static or dynamic.
Professor?
Could you repeat that?
Yeah, would you mind going back to the delta function and the trig, whether it was sine or cosine, and just explain how would you
All right, but
figure it out and solve
I'll
it?
do that in this way.
Thank you.
Yeah. Okay. I'm going to even maybe do an even easier example. Right. I'm just going to set these limits right here. And I'm just, like I said, I'm just making it up. And I have a delta function, and I'm going to delay that by 2. But instead of a sine wave, I'm going to have a step function. Okay. So the thing is we're multiplying these together, right? So this is 0 everywhere else, right? And what we get is we get the delta function times 1. So in fact, it doesn't change, right? So it only exists right at that spot. And so we're integrating a delta function times 1. And so the area would be 1. But let's call this 2, right? Let me choose a different color. All right, I come up, right? That's a value of 2. So now I have, at that moment in time, I have 2 times that delta function, right? So now I'm multiplying this by 2. And so that when I take the integral of it, I'm going to get 2. Now again, right, if I draw a delta function and it looks like it's 10 units high, no, it's really infinity. I would have to kind of put a little symbol here of whatever I've multiplied it by to actually get that. Now, yeah, what would happen if 0 to 10 delta t minus 2 u t minus 3. Right, so here's my delta at 2, right, 0, 1, 2, delayed, but the step function doesn't come up till 3, and so it's 0 everywhere. So 0 times 0 is still 0, and then the area, even though we're within the limits, right, there's nothing, everything is times 0, so it's going to be 0. So now if we replace this with delta t times cosine of t, and let's just say from -1 to 1. Well, this is active at 0, right? This is, and at 0, so at t equals 0, dt equals infinity, oops, and cosine of 0 equals 1. And so I'm going to get 1 times infinity. When I integrate that, I'm going to get the 1. All right. Now, yeah, I could have, if I had different cosines values, it just scales the whatever it happens to be by the delta function, which you see when you do the integration. Okay. So here I have time, and I have a delta function. Right. Delta functions, right, their height equals infinity, and their width equals 1 over infinity, which if the width were that small, you wouldn't see the width of the ink, and a height of being infinity, you can't draw, right? So you'll see in questions, you'll see an arrow go up a certain amount of distance, and it's usually selected so that it looks good on the graph, right? Right. So in this case, you can see that arrow and it's pointing down to -10. That doesn't mean that that is scale by -10. The scale is over here. It's just a drawing convention, right? Because you can't draw infinity. And yeah, it looks like in these examples, I have it always goes up by 10, right? Well, the thing is, and this is just a property, right? The area of a delta function is 1, right? That's one of the properties. So if I, integration is finding the area. So if I integrate, from -infinity to infinity, that area is going to be 1, all right? So what I'm saying is on the plot, it might say 10, but you don't really, you have to look at the equation to see what it is. So delta t, the integral of 2 times the delta function, right? Yeah, this question might show it going up to 10, right? But here it's 2, which is really, and that integration, yeah, it's really, by definition, is 1, and you get 2. Now, sure, if that delta function is approximated by a rectangle, right, it's got to be the height and the width, when multiplied together, need to be 1. And there's other things that we'll go over later. All right. Vicente, did that help or? Okay. Now, just as if I say ft equals, right, and now I'm changing the limit to time, right, I have to change the integration variable to make it a dummy variable. And when I do that, I get a step function, right? Ft of a step function, again, I have to change that variable, right? Gives me RT. And then if I take the derivative, it goes back the other way. Now, really what we're doing is, right now, we have a limit A and a limit B, ut dt. And so we're just finding a number. We're not finding a function of time. So we can keep it all in time. All right. So let's just draw that step function. Okay, it goes up at 0, right? All right. So let's say our limits, right, are between -2 and 1. Well, the step function is 0 the whole time, so that area is going to go to 0, right? Let's make A here and put B here. We call that -1, and this, we'll call that 2, right? I'm going to do that up here. So I'm going from -1 to 2. Ut dt. Now, this isn't like a sign or something. It has a point where it's 0 and then a point where it's 1. And so if you look at it, wait, the function is discontinuous here. So there's a point where it's 0 and then there's a point where it's 1. And what you have to do is break that up. All right, so I have 0, I have, excuse me, -1 to 0, right? And it's 0 at that point, plus 0 to 2, and it's 1 at that point, right? And so really, you know, this is the true width of the rectangle, and that's the true height. And so the area should be 2, not 3, because of the limit. Okay. Thanks for so this is the step function, but many times, because I'm used to device physics, I might write that symbol, all right? And I try to keep it accurate, but it's always step in EE110. This means mobility in device physics in MADI 153. And of course, you know, micrometers or microfarads, but sorry, it's you could call it a nervous tick or something, but I try to write it out. But when I start going quickly, it's hard. So yeah, right here, yeah, you can see where I did that. All right.
But Professor, why is it going up at 0 again?
Could you repeat that?
Yeah, why is it going up at 0 again on the A, B, and then 0?
I mean, from here to here, right, the step function is 0, right? So when you integrate 0, you get 0. Is that?
Oh, okay.
So I'm using these. You know what? Okay, that's the problem we're trying to solve. A equals -1, B equals 2. We have to break that up because the function is discontinuous. Okay. Now, let's integrate RT. So A happens to be -infinity. And then B is 2. Well, kind of by definition of that ramp function, right, it's 0 up until 0. So again, just from -infinity to 0, you're integrating 0. And then from 0 to 2, you're integrating t. All right. Now, where you can get, let's say, eaten up, right, are obviously if the limits are all on 0, it's going to be 0. But if you have limits here, right, you're going to get a trapezoid. But that'll come out in the math. All right. The trick is at this point, right, this RT, when I start at 0, is t. But what if I had, and I know we're going over, but if you have to go, that's okay. It'll be in the video. What if we had RT minus 2? And then let's take it from 4 and minus infinity. So I have minus infinity. I go up to 4. I have RT minus 2 dt. Well, now it's 0 all the way up to 2, just like that step function example we did. And that area is still 0, right? And now we go from 2 to 4, right? But if we just put t, right? T is this equation over here, right? Which will have a much different area than this equation, right? So you can't just use t. You have to take into account the delay. Now then, I don't want to blow anybody's mind, right? But that is equal to 0 to 2 t dt, right? So if I just labeled this now as 0, and then that's 2, well, now that same area is going to be the same area as if I did this, right? And that's what I would call a trick. If you have multiple things, right? You know, I have an RT plus UT minus 2 with a minus RT plus 2. I can do all of these independently and then sum the areas at the end because it's linear. We have 10 minutes. Oh yeah, you got to go to 112, which is a lovely class. So I'll just say, yeah, there's some OPAMP questions on there, but really that's pretty much review. But if you have any questions, just email me and go have fun in 112.
Professor.
Yes.
Yeah, quick question. Do you have like a kind of practice problems before we do the homework, like the integration functions?
The MyOpenMath ones, not really.
Okay.
Right. For the more complicated ones, I'll have something that will be called case studies, and those are old homework solutions, right?
Where do you have those?
Everything's in Canvas, right? So
Yeah.
if old homework solutions exist, it'll be in that module, usually at the end. Okay.
Okay.
So at the beginning of the semester, I do tend to use a lot of MyOpenMath because just like you're coming up to speed, right? I'm trying to deal with add codes and things like that. Where's homework 1B? Yeah, I guess this needed to be changed, but sample. Because I think I deleted I realized one assignment. So sample problem solutions, right?
Oh,
and B. Again, the name is not right, but that's because there was this assignment that really was too much work and I just got rid of it, right? So here's all
okay.
kinds of solutions.
Nice.
All right, and yeah, just, you know, and as a service, right, just since we're talking about it, and okay, so I have previous midterm solutions. If the midterm solution isn't there, it means generally that there's topics that I stopped asking questions for, or maybe I didn't, the solution was correct, but I didn't really like it, right? So I don't, like with Bodhi plots, I've changed some way I do it, and so I don't like my old solutions, right? But yeah, homework 6A, advanced summers, or no, case studies, old homework 6, right? Things like that. Gain bandwidth case studies. So in general, that's where I try to put more solved problems because, you know, there's a finite amount of time we have.
Thank you very much.
All right, guys. So again, all those lab questions and anything, just email me so that I can start to fix all those problems. All right. Thank you so much and have fun.
Thank you.
All right.